Okay, so yesterday we did the principle of superposition, right? Now today we are going to discuss one more parameter in electrostatics, and that parameter is called as the electric field. Now what is electric field? First of all, we need to understand what is a field. Now when you talk about field, I'll give you an example. For example, I'm in the class and there are say 20 students in the class. All of you can understand what I am saying because you are in a space called as classroom, and this classroom has been modified by my presence. Anyone who is outside the room cannot understand what I am saying, right? Why? Because I cannot influence him. He is outside this space. Understood? Now this space which I have modified as per my requirement is called as field. Clear? So inside the field, if there is some other person, he will have influence of me. Is that fine? And anyone who is outside this space, outside this modified field, cannot have my influence over him. Similarly, when you talk about charges, charges also modify the space around them. The modified space around a charge is called as electric field. Is that fine? It is in this electric field, it is in this modified space that other charges can be attracted or repelled. For example, there are two charges. Now this charge modifies the space around it up to some point. For example, this is a charge and it modifies, like for example, this much space around it, okay? This much space. And then there is the one more charge, it has also modified some space around it. For example, this much. If the two modified spaces are away from each other, there will be no attraction or repulsion. The attraction or repulsion only develops when the two fields are close, they interlink. Is that fine? The charges need not to be touching each other. Their fields should be interacting. Is that fine? For example, there is a charge and there is another charge. If I ask you, can they attract? What will you say? Yes or no? I will say no. The reason is, first of all, you have to understand what is the modified space. How much modified space has been developed around the positive charge. Say for example, the modified space is this one. That means up to this point, its influence is present. Okay? Similarly, when you talk about this negative charge, for example, this is its modified space. Are the two modified spaces interlinking? Are they overlapping? They are not. Therefore, they will not attract. For them to attract, what should happen is, this negative, for example, should come here. Because then its modified space will be something like this. And now there is some linkage between the two fields. Understood? And this linkage will result in the force called as the attractive electrostatic force. Is that clear? Do you understand what is field now? Field is the modified space around anything. For example, you have a magnet. Have you played with magnets? When the magnets are far away, do they attract? When you bring them closer, do they attract? But there will be a point when they start attracting or repelling, right? Before that, they are here, nothing happens. But when you get them close, up from some point, you can observe attraction or repulsion, isn't it? That is again a modified space, but that modified space will be called as magnetic field. Is that clear? Fine. Here we have what? The electric field. Why? Because now the Jamal has arrived. Just 15 minutes late. Is it clear? Do you understand what is field now? Okay. Now, because this field has been generated by electric charges, be it positive or negative, we called it as electric field. Fine? Now, whenever you talk about electric fields, now there is some important thing. we talk about the strength of electric field. What is the value of the electric field? Okay, how do we do that? See, for example, we have a source charge here, and then it has a modified space. Say, for example, this is the modified space. Okay, inside this modified space, I am bringing a small charge plus Q. Inside this modified space called as the electric field, I am bringing a small charge plus small q. Okay, what will happen? Will they attract or will they repel? Yes, will they attract or will they repel? This is also positive, this is not negative. They will repel. That means, see, this source charge will not move because it is big enough. Okay, it has more mass, so it will not. But this charge has a tendency to move because it is very small. So what will happen is this charge will be repelled like this, isn't it? Yes. Isn't it? So remember, in order to understand the strength of the electric field, we want to calculate how strong is the electric field developed because of capital Q. That strength is calculated by the force that this charge experiences divided by the charge. Is that fine? The force that this charge experiences divided by the charge. That means, I'll tell you, if you have to calculate the electric field at this distance, for example, the distance is R and the point is P. Okay. You want to calculate how strong is the electric field of capital Q at point P. So what you will do is, you will bring a small charge and keep it at small p, keep it at P. Okay. And then you calculate the force. Can you tell me what will be the force between the two? Yes. What will be the force between the two? You know it as per the Coulomb's law. Yes. Is it gamma Q small q upon R squared? Isn't it? This is the force. But if you take this, which implies, can I say force divided by small q? Force divided by small q. What will be it? Yes, gamma capital Q upon R square, isn't it? Now this thing, the force per unit of charge. Force per unit of charge. Which charge? The charge that I kept here. This is called as the electric field strength. Is it clear? This is the expression for the electric field at any point. If you want to calculate electric field at this point, say this point is Q, say this is X, okay? If you want to calculate the electric field strength here, find the distance, let the distance be R1. Then use the expression again. Yes?
What's under RQ? No.
R square?
Yes, what is this?
R square? This is electric field, okay? So if you want to calculate electric field at this point X, what will be the expression? The electric field at point X will be equal to the same expression. Gamma Q, because the original charge is Q, divided by, yes, the distance square. What is the distance now? R1. So distance R1 square. This is your electric field at this point. So different points will have different electric fields. The strength will be different. See, I'll tell you, someone who is at the front, for him, the intensity that I'm speaking with is more, isn't it? But someone who's at the back, the same intensity becomes low, isn't it? Similarly, electric field is more, it has more strength when it is very close to the original charge, and when you go away, it is less. It is fine? Here it is more, here it is less. Because after this point there is no influence, there is no modified space. So modified space starts from this point and it decreases radially outwards. Is that clear? When you go out, when you go away, the strength decreases and there is the electric field is zero outside the boundary. So therefore it must be maximum here, and when you go out, it must decrease. Is that fine? Is it clear? Now what is electric field by the definition? Yes, it is force per unit of charge, isn't it? Isn't it? Now if the charge is positive, what will be the direction of the force? Is it outwards? Yes? So remember, from today onwards, electric field is shown by lines, but for a positive charge, they are away from the charge. Why? Because electric field is the force and the force is outwards, isn't it? From a positive charge, it is away. Okay? But for example, this charge here was negative. What would have happened? If I for example do this, for example I do this, there is negative charge here, it has a modified space, this is a modified space, and I bring another charge, plus q here. What will happen to this plus q? It will be attracted, right? So attraction will be something like this, isn't it? Yes. So if I calculate the force per unit of charge, that would be gamma capital Q upon R square. Say the distance here is R, okay? Now this is the electric field, but due to this charge, okay? Now this charge is negative, force is attracting, so therefore the electric field will also be shown towards the negative charge. So from today, whenever you have to draw the direction of the electric field, because electric field is also a vector, okay, the direction will be shown. For positive, show the lines are going away. For negative, show the lines are coming towards or into the negative charge. Is that fine? Yes. Write it down. I'll make you write some things. Electric field is the modified space around a charge. Is the modified space around a charge in which modified space around a charge, okay, in which other charges can experience attractive or repulsive forces. Okay? Full stop. Point number second. The strength of electric field is defined as the force experienced per unit of charge at a point inside the modified space. At a point inside the modified space. Okay? Full stop. Just write this diagram. Show this diagram first. Plus Q, then small plus Q, and then we calculate this, and this is electric field. Write this down. Because the expression is important, we have to solve the numericals. Electric field for a positive charge, plus capital Q, you place some small charge plus small q at point P, which is at a distance of R. So you calculate the force, and then you calculate force per unit of charge. This is electric field, gamma Q upon R square. Okay?
We just do the point Q and point P and around it.
Yeah.
The other thing done.
You don't know. You don't need. This is an example. I can erase this. Fine. Is it fine? See, this point is very important. Very important. When the charge is positive, this charge goes away from the positive charge, isn't it? And when the charge is negative, okay, then the point charge that you have brought inside the field will come towards it, isn't it? So remember, write the point. For a positive charge, electric field is away because it is a vector quantity. The direction of force is away, isn't it? So for a positive charge, the force is away, therefore electric field is away. Okay? For a negative charge, electric field is inside. Why? Because the force is attractive. Okay? For a positive charge, electric field is away. Electric field is away. While as for a negative charge, it is towards the charge. Okay? Fine?
Yes.
Okay. So now we have some numericals. Before I take up some numericals, I want to tell you something about the force experience. See, very important. For example, I have a source charge, okay? It will modify the space around it, isn't it? Let the modified space be this. This is the modified space, okay? This is the modified space. In this modified space, if I keep at a distance of, say, at a point P, which is at a distance of R, okay? If I keep, can you tell me what will be the electric field at point P? Yes? Electric field at point P due to this charge, yes? The expression will be gamma capital Q upon R square, isn't it?
Yes.
Isn't it? At the same time, if I keep the point P, if I keep a small charge here, small charge, will there be the electrostatic force between Q and capital Q? Yes or no? Yes. Why? Because it is inside the field, isn't it? What will be the value of the force? What will be the value of the force? Yes? Gamma Q upon R square, isn't it? Yes or no?
Yes.
So, if you check gamma Q divided by R square, this, isn't this electric field? Isn't this electric field? So, can I say that the force which is between the two, or the force which this charge experiences, is given by this charge Q multiplied by E? Can I see this?
Yes.
Yes or no? Yes? Now understand the direction of the force. If this charge is positive, what is the direction of the electric field? Away? Isn't it? And away means something like this? Yes? And what is the force between the two? If this is positive, this is positive, what will happen? What will be the direction of the force? Repulsive. So it will be same, isn't it? Force and electric field are same, isn't it? So see, what is the direction? The direction of the electric field is equal to the direction of the force when this charge is positive. But if you place a negative charge here, electric field was like this, isn't it? Because electric field is due to this, which is away. But what will happen between these two charges? What is the force? Is it attractive or repulsive? Attractive. So the force is here, isn't it?
Yes.
So it means when the charge is negative, the force is applied against electric field. When the charge is positive, force is applied along electric field, isn't it? See, try to understand it from the diagram. When this charge is positive, see, electric field due to this is always away. For a positive charge, electric field is away. That is what you wrote. Fine? Now electric field is away like this, like here it will be like this, here it will be like this, here it will be like this, here it is like this, okay? Now what I do, I keep a small charge here which is positive. Now there will be repulsive force between small q and capital Q. So the force will also be outwards. So the force and electric field have the same direction when the small charge is positive. So that means when this charge is positive, force and electric field will have same directions. Is it clear?
Yes.
But when the charge is negative, now I place for example a negative charge here. Electric field is outwards, isn't it? But capital Q and negative small q, they will attract. Attraction means force will be towards the capital Q, isn't it? So force is against electric field, isn't it? I place a negative charge here. Electric field is outwards, but the force will be towards the positive charge, isn't it? So force is against the electric field when the charge is negative. Is that clear? Write it down. If a charge is placed inside electric field, if a charge is placed inside electric field, it experiences a force. If a charge is placed inside electric field, it experiences a force. Okay? It experiences a force given by, write this expression, direct. F is equal to QE. It experiences a force. F is equal to Q times E. Is that fine? Fine? But write a point. Another point. If the charge is positive, if the charge is positive, force and electric field have same direction. And if the charge is negative, if the charge is positive, force and electric field have same direction. Okay? But if it is negative, force is applied against electric field. Force is applied against electric field. Is there any doubt in this statement?
If it's negative,
Force is applied against
force is applied.
electric field. Is that fine? Now see. I have shown electric field here. This is electric field. Okay? It is from left to right. Okay? I place two charges inside. How many charges? One is plus small q and the other one is negative small q. Can you tell me what will happen to these two charges? Yes, very good. Yes. What will happen? To plus q, the direction of the force will be? For plus q, yes, what will be the direction of the force? It will be same as that of electric field, isn't it? So it will go like this. Okay? And the force will be given by QE. Is that fine? But what will happen to negative Q? Yeah, it will be against the electric field. So force, it will be again Q into E, but the direction is against the electric. Is it clear? This is the point. Draw this diagram so that that point gets clear. Fine? Okay?
Is it just QE that is in the opposite direction?
Yeah. QE. the charge is negative, it is minus QE as per the directions. Minus means the direction is opposite. Otherwise, magnitude of the force is Q into G. Fine? Okay. Okay, then we have a question now. Let us try to solve this question. How are electric and gravitational fields similar? So you know the force of gravity, right? Between two bodies. What is the force of gravity between two bodies of mass m1 and m2? Anyone? Yes? There are two bodies, one is m1 and the other is m2. They are separated by some distance r. What is the gravitational force between the two? Yes? F is equal to? You know this expression? G m1 m2 upon r squared? How many of you know this? You done it? This is gravitational force, right? Newton's universal law of gravitation. When there are two bodies of some two masses, okay, there is gravitational force between the two. But if you understand electrostatics, there are two charges, capital Q and small q, separated by some distance r. There is force, isn't it? And what is the force? Gamma q upon r square, isn't it? The question is, this is electrostatic, isn't it? And this is gravitational. The question is, how are these two fields similar? What similarity do you see in these fields? What similarity do you see between the gravitational force and the electrostatic force?
R squared.
R square means? So the first point, right? The first point. Similarity between gravitational and electrostatic fields. First point. Both the fields follow the similarity between gravitational and electrostatic field. Salam, Dorale. Similarity between gravitational and electrostatic field. Point number one. Both the fields follow inverse square law. Isn't it? Inverse square, see? Both in the denominator, see what does that mean? That means if you increase the distance between two charges, what will happen to the force? If you increase the distance, what will happen to the force? Decrease. If you increase the distance, what will happen to the force? And it decreases in the same way.
What's the fixed for inverse law?
Inverse square law. Is that fine? Both decrease and both decrease in a similar way. Here it is square, here it is also square. Is that fine? Any other thing that you can say about the gravity?
Both have constants. One is.
Both have constants, but the constants are not same.
Both measure the distance between the two objects, Q1 and Q2, and then M1 and 2.
Mm-hmm.
Yeah,
Right.
capital Q.
What is the similarity? Okay, tell me. If this is M1, this is M2, do they attract each other? Yes? Because of the gravitational force. So, does that mean M1 is asking M2 to come towards M1? And does it also mean that M2 is asking M1 to come towards M2? Isn't it? So, how will they move? Will they move through this straight line, center to center? Yes? Isn't it? Similarly, when you talk about the electrostatic force, if you have two charges, okay, they want to repel or they want to attract. So what happens is, if they attract, they will come along the same line, the center line. If they repel, they will repel along the same line. Is that fine? Write down the point. Both the forces are central forces. Both the forces are central forces. That is the force acts along the line joining the two charges. Joining the two charges or bodies. Is that fine? Do you understand what are central forces now? Central forces are the forces which act along the line joining the two bodies. Is that fine? Center to center. These forces are not like, if this is M1, this is M2, they won't act right. It's not like M2 will go like this. No. It's not that M2 will go like this. No. It goes straight. It goes through a single path, and that path is the line joining the centers of the two bodies. Is that clear? Similarly, electrostatic force. If it is repulsive, if it is attractive, doesn't matter. It always acts along the line joining the two. Is that fine? Third important point. Write it down. Both the forces are conservative forces. Can you tell me what are conservative forces? Anyone? Both the forces are conservative forces. Yes? You have done. I thought he will define conservative force. He's asking me to put on the AC. Yes. Both the forces are conservative forces. Anyone who can explain what do you mean by conservative forces? What are conservative forces?
Forces that get conserved.
Forces that get conserved. Okay, I give you a question. Let me give you a question. For example, this is Burj Khalifa. Okay? And there is Hiba. She wants to be on the top. The height of Burj Khalifa is h. Okay? Is that fine?
Yes.
Hiba wants to go up. So, and there is one more. Say there is Tagreeb. And I can put Mr. Maid as well. Okay? Hiba manages to go to reach the top of Burj Khalifa with the help of a lift. She goes into the lift, she's very smart. She goes up, lands there. So this is Hiba now. She's like, how are you all? I'm here. She can see the whole Dubai from Burj Khalifa. Okay? But then Tagreeb, her father tells her, you don't need to go through the lift. You are my daughter. You take a helicopter, go direct like this. And she's like, oh yes, that's a better way. Okay? She reaches the same height. Okay? Now Tagreeb is here. She feels more proud, you know. She's like, I spent more money reaching the top. But then there is Mr. Maid. He doesn't have any money. So he asks me, sir, how do I go? I tell him the best way to reach the top is by climbing a ladder. He takes all the time in the world and reaches the top. Now Mr. Maid, sweating, drained, exhausted, he's also at the top. He's also happy because he has achieved the feat of climbing Burj Khalifa, isn't it? If I ask all of you, who has done the maximum work? What will you say? Yes. Don't you think you have done extra? He doesn't believe he has done more work, see? Yes, anyone? Who has done the maximum work? Why has Tagreeb done more work?
She spent more money. It takes more energy to reach it.
It takes more energy. That means petrol. That means money. Dirhams, okay? Tagreeb has done more work. She did nothing. Hiba? Because she took some steps, pressing the button and going in. Huh? Remember, all of the three have done the same work. Work is not more or less here. Because work is being done against a force called as the gravitational force. The gravitational force for all all of them are doing work against this force. Is that fine? And you need to understand that when all of them reach this height h, can you tell me what is the change in the potential energy? What is the potential energy at the top? Yes? Is it mg multiplied by h? What is the potential energy of mine? Is it mg ladder h? Or is it h? What is the potential energy of Hiba? What is the potential energy of Tagreed? mgh, isn't it? So potential energy is same. Work which all of them have done is equal to the change in the potential energy, and that is equal to mgh. Work is being done against the gravitational force. Now you see 3 people taking different paths, but the work of all the people is same. Such field against which the work is done is called as a conservative field. That means it is immaterial of the fact which path you choose. Is that fine? It doesn't depend on the path. The work is independent of the path. Work depends on where Maid was and where he is now. Work depends on where Tagreed was and where she is now. Work depends on where Hiba was, where she is now. It doesn't matter if Hiba was like this. Doesn't matter. Work is again the same. Because here the work is being calculated against the gravitational force, and gravitational force is a conservative force. Work is independent of the path. It depends on the initial and the final positions. Is that clear? And because the initial and final for all of them is same, work done is same. Is that clear? Similarly in electrostatics, if a charge is moved inside the field, it doesn't depend on the path. It depends on initial and final positions. Is that clear? This is the definition of a conservative field. Conservative field doesn't mean something is conserved. Write it down. That is, what did you write? Both the fields are done. That is, the work done is independent. That is, the work done is independent of the path followed. Work done is independent of the path followed. Full stop. It depends on the initial and the final positions. It depends on the initial and the final positions. See, now we have a charge, source charge, okay? There is a point P and then there is a point Q, and you want to take this small charge from P to Q. You can take it in any way, right? You can take it like this, you can take it from like this, or you can take it direct. If I ask you, this is 1, this is 2, and this is 3, along which path is the work maximum? Same. Work is same. Because we are talking about the work which is being done against electrostatic force. Electrostatic force is a conservative force. Therefore, work through 1, 2 and 3 is same. Because initial and final points are same. Understood now? Is it clear? Conservative fields? Fine? Draw these 2 diagrams too. You won't forget Hiba ever now. Sorry, Mike, don't feel bad. I told you don't have money. I know you have, it's fine. You feel bad. Please think about why it's that big you don't have money. Abdullah. Late. Oh, you're very early. Just 10 minutes.
Please attendance.
Ah, he comes for the attendance. Is it clear? So, are the 3 points of similarity clear to you guys? They are the similarity points, okay? Now, if I ask you, what is the difference? How do they differ? Yes? How do they differ? How are they different? How are they different?
They measure different things.
They
Measure different things.
measure different things. We know that one is gravitation, another is electric. We know that. How are they different? Exactly, the constant. See, the constant here G, it has a very small value, 6.67 10 raised to the power minus 11 Newton meter square per kg square. But here gamma, the value of gamma is yes, 9 into 10 power Newton meter square per coulomb square. So this is the reason I gave you the ratio of the 4 fundamental forces, remember? I told you electrostatic force is much more stronger than the gravity. It's the weakest force. It is stronger force, 10 raised to 39. Is that fine? So, point number 1. The constants are different, due to which their magnitudes are different. The force, if you talk about, for example, you talk about an electron and a proton. Okay? Electron and a proton. Let us try to solve this question here. You have an electron and you have a proton. They are at a distance of 1 meter. The question is, can you guys calculate electrostatic force between them? And can you guys calculate the gravitational force between them? What is the gravitational force? It will be because of the mass, isn't it? And what is the electrostatic? It is because of their charge, isn't it? Can you calculate it? I will give you all the values. You try to calculate it. So gamma, you know, it will be Q1 Q2 upon R square. But for this it will be G M1 mass of electron mass of proton upon R square. So the distance is 1 meter. I will give you all the values. The charge of an electron is equal to the charge of a proton, and that is equal to 1.602 multiplied by 10 raised to the power minus 19 coulombs. Okay? Then you have the mass. The mass of electron is equal to 9.1 10 raised to the power negative 31 kgs. And the mass of proton, it is equal to 1.67 into 10 raised to the power negative 27 kgs. Put in the values.
Can you put the value of R?
R is 1 meter.
Not the
Gamma?
Yeah.
Gamma is 9 into 10 power 9. And G is 6.67 multiplied by 10 power negative 11. Yes, put in the values. Give me this, give me that. I'll show you the difference between the two forces. We calculate the electrostatic force and the gravitational force between the same two entities, isn't it? We change nothing. But let us see what will be the electrostatic and the gravitational force.
This one is Q1 and Q2.
Yeah, Q1 and Q2.
Can you do a
Allah, multiply. You square it, whatever is there, square it.
For electrostatic force, it's 2.3.
For electrostatic force, it is
2.30
2.3
times 10 to the power negative 28.
10 to the power negative
28.
28. Okay, and what about FG?
1.01 times 10 to the power of negative 62.
1.01
01 times 10 to the power of negative 60.
negative 60. This
62.
62. Positive or negative?
Negative.
Okay, now next step. Find this divided by this. FE by FG. Find FE upon FG. FE upon FG. FE upon FG.
That's negative 60.
FE upon FG.
2.28.
Uh-huh.
2.28.
2.2.
86.
86.
Times 10 to the power of
10 raised to the power
34.
34. See what that's what I was telling you. Because the value of G and gamma is different. See, G is so small, 10 raised to the power negative 11. And gamma is so big, 10 raised to the power positive 9, isn't it? The reason is this, due to which the electrostatic by gravitational 10 raised to the power 34. So we can say electrostatic force between these two is 10 raised to the power 34 times stronger than the gravitational force. It is just because of the change in the constants. Is that fine? Clear? Write it down. Write this down. Because of the variation in the constants, the electrostatic force, because of the variation in the constants, the electrostatic force between electron and proton, because of the variation in constants, the electrostatic force between an electron and a proton is 10 raised to the power 34 times electrostatic force. The electrostatic force between an electron and a proton, is 10 raised to the power 34 times stronger than the gravitational force. Is 10 raised to the power 34 times stronger than the gravitational force between them. Is it clear? Yes? This is one of the difference. Any other difference that you can tell me? Any other difference? Think. Gravitational force is like your mother, Ummi, always loving. She doesn't hate us, right? Gravitational force is always attractive in nature, isn't it? But electrostatic force is like your father. Sometimes he taunts you, sometimes he loves you. There is repulsion as well as, isn't it? Gravitational force is only attractive, while as electrostatic force can be attractive as well as repulsive. Write it down. That's another difference between the two. First was the constant, and the second is gravitational force is always attractive, while as electrostatic force can be attractive as well as repulsive. Is that fine? So from tomorrow we'll be solving some numericals over this, but you can take a picture of this. This question is your homework. This question. Example B. We do it tomorrow. Is that fine? Okay, thank you very much.